Hello, welcome to this video where I'll go through the advanced random numbers notebook, which has sort of two separate sections. The first will talk about sort of an actual method for generating random numbers. It's not so that you should go out and use it when you want random numbers. You should still use NumPy or SciPy because those are sort of faster and easier to use. But this is just to show you sort of, and I give you an idea of what's under the hood and what the computer does when it generates random numbers. So it shows you a simple method of how that could be done. The second section is called Gauss-Hermite quadrature, and it sort of relates to this numerical integration stuff where the easiest way to do it is Monte Carlo, where you just sort of generate random numbers and then emulate the distribution from that. If you just want the mean, for example. And Gauss-Hermite is a different method of doing this, which is slightly more advanced, but also more efficient. And we'll get to it when we get to it. First, we'll start with the first section. A middle square method for generating random numbers. So one way to generate random numbers is to start with an n-digit number. So there could be a 4-digit number, 5-digit number, and then you take the square of that number, pad it with leading zeros to make sure that it's now 2 times n digits. So when you square it, it's of course going to be larger, but maybe it's not going to have twice as many digits as before, so you pad it with leading zeros, and then you extract the middle n digits out of that. And that's sort of a pseudo-random number. Because, of course, if you know the calculation, then you can sort of, from this number, you can calculate this number. So the sheet gives the number, but it's sort of pseudo-random. That's not like any process that's directly, you can't sort of anticipate the next number in the sequence without actually doing the calculations. So in that way, they are random. And then you can return to step 1 and generate one more random number. So the pro is that this is relatively simple to understand and to explain, and it's conceptually similar, somewhat similar to some of the methods that, for example, NumPy actually uses. The con with this exact method is that so a cycle, it's each iteration, so each new random numbers, and a cycle cannot be longer than 8 to the power of n periods, and sometimes it will be even shorter, because sort of a cycle ends if you generate the same random number, and also it ends if you generate the same random number, and this can happen if you just accidentally hit the same random number, because then if you do that, then each cycle will sort of repeat itself, because if you get to the same seed number here, then it will sort of be a deterministic process given your previous cycles. And you can also just hit 0, and if your number is 0, then your next number is also going to be 0. And some of the cycles can be very short. If you start with a number that sort of gets itself out, then the cycle is one cycle. Or one period. So it's not something you should use in practice, but it gives you an idea of what sort of happens when the computer generates a random number. So this is the function that actually does it. And we have to keep a list of the numbers we have already seen. So in order to, if we get these sort of repeating cycles, then we want to stop generating new random numbers. And then we just have a loop which sort of just keeps on going for 100 iterations, or if the number has already been hit before. And then we just do the calculations. So we add the number to the list of C numbers, and then we calculate the new number by squaring, adding leading zeros, and extracting the middle 4 numbers. So this is an implementation for 4 random digits. Yes, and this is sort of how it looks with a lucky good seed, where you get lots of random numbers. So these are the numbers that we get out. So you have this print where you print the square number, the padded number, and the extracted middle 4 digits. Yeah, and then you can see this sort of repeats, and it gives a lot of numbers that varies a lot, so they look perfectly random, and that's good. But you can see that at some point we get to a low number, and that number sort of is too low in a sense. So you get to 0, and then you have a repeated number. So that number is no longer good. But you can use all of these initial random numbers. But of course, if you choose an unfortunate seed, then you can get a short cycle because you hit the same random number. So we start out with 540, and then we get 3 numbers, but then the 4th number that we get out is the number that we started with. So we're going to get the same repeated cycle again and again. You can also have a number that sort of outputs itself. So if you start with 3792, then the square is this large number, and it doesn't need to be padded. But the middle 4 digit is the number that we started out with. Yeah. So this is not actually practical, but in essence, it's something like this that Python does to generate random numbers. And I think it's nice to see this, sort of to understand, okay, it's not true random numbers we get, but we get some pseudo-random numbers, some weird numbers out from some calculations. The Gauss-Hormite quadrature is something that you're going to be using in practice, or maybe not something that you are going to be, but it's very practicable. And if you take advanced programming courses with advanced models at KU or at another university, then it's probably something that you're going to be using. Yeah, so the issue with the Monte Carlo stuff is that it's slow, and the solution is to use Gauss-Hormite. Yeah, it's not, Gauss-Hormite is one implementation. Then the solution in general is that you can sort of, instead of just having a bunch of observations here, which was the Monte Carlo way, so draw a lot of random numbers, and then you sum those together. The solution here is to say, okay, we know the distribution that we're trying to emulate. What if we, instead of just drawing random numbers, then we say we draw a specific set of numbers from the distribution, and then we take a weighted average from those numbers that we have drawn, which emulates our distribution, but we don't need like 100 different points. So from a normal distribution, then you would sort of take points along the normal distributions, and then the numbers on the edge of the distribution you have to give a low weight, and the numbers in the middle of the distribution where there's the most mass, you would give them a high weight, basically. And Gauss-Hormite is one way to determine what the numbers you should be drawing should be and what the weights should be. Yeah, and sort of the Gauss-Hormite way is a theoretical formula, which I'm not going to get that much into the specifics. You can sort of, there are some links here if you want to try to understand it a bit more, but it's really not for practical purposes. It's not that important to know exactly how the formula has been proven or how it has been extracted. It's just important to know how it works, sort of that it gives the right answer and how you make it give you what you want. So we just have a small example here for a normal distribution and a function, the same function that we used that we have used before, x minus 2 squared. So how does this look? Again, this is sort of the formula for how you derive the Gauss-Hormat weights and nodes, which are the values. As I said, you can sort of use this links to sort of a bit get an idea of what is happening. But the base thing is this, that you're sort of calculating what sort of nodes you want depending on how much precision you have. So you have the same as with Monte Carlo, that if you increase n, then you can of course get a more precise estimate. But for nicely looking functions, then you need a lot much lower n. So this function implements that. Both the weights and the values, and then this is in the normal case, so a normal distribution for a given sigma, and you can also change the mean, the mu. You can change how many nodes you want, and you can change if you want it to be a log normal distribution. This is a small if statement just to ensure if you want sigma to be 0, so you have no standard deviation, then you would just have the same number always, the mean. Or if you only want there to be one node, then you also want that node to be the mean. So we draw the Gauss-Hormat nodes and weights. Then we adjust them again according to a formula, and this is because we want the Gauss normal distribution. So we adjust them according to the standard deviation. And this is if you want log normal, then you need to do a bit more. You just need to. This is actually the same as taking a function, because I'll show you the log normal stuff afterwards. So just ignore this first. So if it's not log normal, then x is just x. Of course, if you want to change the mean, so right now the mean is 0. If you want to change the mean, then the function does that. And then you need to re-weight the weights. So we want this, and then we define our g function, define a mu and a sigma, and then this sort of prints. I think I forgot to run something. So this prints the results for how many n's we want. So we can see that, okay, if we choose n equals to 1, then we get a very imprecise estimate. But already with the 2 nodes, then we actually get an extremely precise estimate. Because already at 11, then you're certain that this is the correct answer. This is only because it's a very nice function that it goes this fast, but in generally you don't need that many. But of course depends on how nice and how not nice functions you're using. I think what I mean by nice, and this is because you can sometimes if you want to emulate a distribution of agents, then you're sort of solving the agent's problems in a non-analytical way. So this g function could be something like an agent optimization problem, so the solution to that. And if it adds king points or jumping points, so it's not continuous and all those kind of stuff, then it's going to be more and more important to have more and more quantitative points. Then the log normal case. So log normal distribution is just a distribution which is normal after taking the log of it. And the way you can calculate that is just by taking e to the power of a normal distribution. Because if you log e to the power of something, then you get something. And the function you just set x to be equal to true. And what happens here is just that if you haven't specified a mean, then the function just ensures that the mean of the log normal distribution is 1, which is not by default. Because when you take this exp, then the mean of exp to x is not the same as exp to the mean of x, because that would be 1, because you have a mean of 0 and exp to 0 is 1. But sort of the standard deviation matters for the mean of x of distribution of x. Yeah. And you can also sort of see that. So if you change sigma here, then the mean will also change for this first function. Or maybe I need to put it before. So this is just comparing with the Monte Carlo version, which would be you just draw random numbers. So for example, when I increase sigma, then I'm also increasing the mean of the log normal distribution. Or not of the log normal distribution, but of the log normal distribution, sorry. That was the main part. So Gauss Hermite is not really a direct part of this course. If you want to use it in one of your assignments, you're very welcome to. If not, then this was just a quick introduction to video. So when you learn about it later, then you will have a slightly head advantage if you learn about it later. If you take more of these advanced Python courses or advanced programming courses in economic modeling. Yeah. So thank you for watching.